Good morning, everyone. This is Praneet Kuber. I'll be presenting our paper titled End-to-End Point Cloud-Based Generative Model for Multi-Part Engineering Designs. This paper has been authored by four of us, Gaurav, Ameya, and Varun, in addition to me. So in this presentation, we'll be going through, first of all, the introduction, what point cloud data is, and its few of past implementations using deep learning and various challenges faced in that regard. Then we'll get into the problem statement that we took for ourselves and some of the synthetic data that we use to train our models. Then I'll get into the related work done in the past from which are really interesting reads and from which we got heavily inspired to carry on our work as well. Then I'll get into VAs. When I say VA, it's a variational auto encoder on the artificial data that we created for ourselves. And then I'll get into experimental results, and I'll finish off with the conclusion and the future scope of this study. Yeah, so starting off with point cloud data. So what this data is, I'm sure if not all, some of us might have used this kind of data in our prior works. So this, as the name suggests, is just a cloud of points in space, or maybe an arrangement of points in plane. And this data is characterized by the x, y, z coordinates of every point in space, or just x, y coordinates in the plane. And every point is a fundamental building block of this entire data. Then other attributes may include color, reflectance, or the object class for individual point. There are various acquisition methods for this kind of data, including photogrammetry, where various images of an object are taken from multiple angles and stitched together, and then triangularized to generate points out of them. Then there are time-of-flight sensors like radar. LiDAR is one of the very popular method. And then there are some engineering design tools as well, which generate the exterior geometry of an object, and then subsequently it is discretized. The surface is discretized, and various points on the surface of the object are accumulated in the form of a point cloud. The applications of this kind of data include depth sensing cameras, obviously. Then gaming consoles which have motion tracking features, and then obstacle detection in the applications like self-driving cars or the robots that you can see walking on the floors of plants in certain manufacturing industries. Then there are certain challenges associated with this kind of data. First of all, the data volume, because sometimes it's not just an object which is represented with this with point clouds. It sometimes can be entire scene, or maybe even a collection of scenes stitched together. Then due to various ways of acquiring this data, or its transition from the source to another storage method or so, it may also include some noise and various other artifacts which get generated during the stitching of multiple point clouds. And then the registration of multiple point clouds from multiple sources also introduce some noise in this kind of data. Then coming to its application in deep learning that has been done so far. So first of all, when we say point cloud, or when we visualize a point cloud, it's since it is scanned from the surface of an object, it's just the arrangement or just the distribution of certain points on the surface. But when it is stored, it's just kind of a tabulated data or array structure. So which in itself does not have any feature. It's just list and potentially even unordered, and the order may get messed up when this data is transferred from one source to from one storage to another. What we see on screen is just the plotted representation of this data, and in the past, various popular architectures have attempted voxelization of this kind of data to be used in deep networks to extract the features. So when I say voxelization, it is just a 3D form of an image, or 3D form of a mask. If you guys are from computer vision background, it just fills the volume in the space. It just fills with a cell in the space with certain volume if there is a presence of a point. And the downside of this, though this is a ordered grid-like structure which can be read in a deep network and features can be extracted easily. There is a downside of this kind of data. Here, the memory consumption is really high, and sometimes the density of point clouds is not captured well because of the discretization details. And then there are also loss of finer details when there are like curvatures or relatively smaller features. And these models are also computationally very expensive owing to their size in deep learning models. So coming to the problem statement that we had for ourselves, so we wanted to have a generative model which could generate compound shapes. Majorly, most of our engineering applications have compound shapes where multiple parts have certain relationship within them. So we wanted to have a model which could generate individual parts and also maintain the relation between these parts so as to form a feasible compound shape. This is just a representative picture. We had done this on our internal data, but owing to its sensitive nature, we have also conducted this study with very simple geometric shapes to publish it in a public forum. What you see on the screen, it's just arrangement of certain geometric shapes, namely ellipse, a rectangle, and a triangle, having certain relationships within them. And we have tried to, this entire data set has a random affine transformation of these shapes, but the relationships are held true in all of the samples of this data set. Coming to the related work, we have referred to a few papers, most interesting of which were PointNET. This is an architecture which deals specifically with point cloud. It kind of extracts the important features out of the point cloud. It is characterized by their contributions, namely TNet and the max pool layer, which are respectively responsible for making the network insensitive to any affine transformation present in the data, and to preserve the permutational invariance. By permutational invariance, I mean sometimes the sequence of the points may not be exactly same, but the object contained within the data is essentially the same. So this the max pool layer and the TNet in this architecture are responsible for preserving these two very important characteristics of the data. So as you can see, there is a representation of the points which were retained by the network after the output of max pool layer is generated. These essentially form more or less the skeleton of individual objects, and it can be conclusively said that the network is successfully extracting meaningful features from the available data. Then there is another architecture called SDM-NET. Here, what they have done is they have created multi-level variational auto encoders to somewhat similarly do what we are also doing. They have individual auto encoders for individual parts. They like to call it part VAE, same as we do. So these part VAEs are responsible for generating individual parts of the assembly, and then there is a shape VAE, which is the second layer of the second level of the VAE, which is responsible for maintaining the relations between the part. But here what they have done is this is not the entire solution of their contribution. After the parts are generated by the individual part decoders on the other side, and from the latent spaces of the individual parts generated by the decoder of shape VAE, they also have an optimization step, which is sort of a post-processing step when the data is generated by or data is given out by their architecture. Coming net, we also trained individual variational auto encoders for individual parts, and as an initial attempt, we tried to just concatenate the outputs of every part decoder, and we saw, obviously, as we can see here, though the generation was reasonable, but the relations between the parts were not held, and we could see a major loss of relation, which was not what we expected. Coming to the architecture that we as we progress, as the architecture that we developed as we progressed, we have individual part VAs, and their latent spaces are fed as an input to a shape VA similar to SDM-NET. In addition to that, we have a structural embedding autoencoder, which essentially has certain other features from the entire sample of a data set, which was additionally done by SDM-NET when they got the outputs from the decoded shape or decoded geometry. We tried to eliminate the need of that post-processing optimization step by including this structural embedding here, and despite that, there were a few areas or a very minor loss of relation details. To combat that, we had added an attention layer to capture the finer details and come up with a reasonable generation. What you see here on the screen is one of the reconstructions from our data set, and we can see that the reconstruction is almost a one-to-one match in terms of the affine transformation of the geometry in itself. Secondly, maintaining relation, and also at or every corner, or very finer details of the shape were captured in this way. In addition to that, we had done few experiments with beta annealing, where we vary the weight which we give on the regularization term of the variational autoencoder, where it tries to fit the distribution close to a Gaussian. With that, the outcome was I'll discuss that in my coming slides. So first of all, our first contribution is the PointNet architecture, exploiting the PointNet architecture for multi-part structure that we had not seen in the past being done. Second is the use of structural embedding to learn interpart relationships. This particular technique eliminates the need of post-processing or the optimization step that is mandatory to be done after the reconstructions are, or the samples are generated from the end decoder. Then we have this attention block that we kept in the structural embedding to capture finer relation details. And then there are some experiments that we did with the beta annealing, where we vary the weight either linearly or cyclically on the regularization term of the variational autoencoder loss function. So coming to the experimental results, so here we have, though the visual inspection of such experiments is mandatory, but we also wanted to have certain a quantitative measure for us to get a reasonable direction. We tried to calculate the FID scores for the distributions of the original and generated data, and we could see gradual decrease. At times the decrease is sudden, but we could see progressive and gradual decrease of the FID scores, which told us that we are going in right direction. And also with the results from the final samples, we see that whatever we wanted to achieve with this network had been done. So coming to the conclusions of this study, we conclude that the VAs are really good candidates when it comes to generating point cloud data, and the proposed network, it learns the interpart relations, so we eliminate the need of a post-processing step or an optimization step at the end of the decoding step. Then the third point is sort of covered in the second itself. And since this point cloud does not have any specific shape-specific needs, it can be scaled to any multi-part engineering design as long as it is represented in the point cloud form. And as part of future scope, we have also attempting architectures like diffusion model, though we have not concluded anything out of it yet. And in addition to PointNet, there is another architecture called PointNET++, which hierarchically extracts the features. So inclusion of that also can be attempted in future. So that's all from my side. Thank you so much. I'm open to questions if any.